Thank you, Felipe. Thank you very much for the invitation. It's my pleasure to be back in IMPA. And I have kind of the feeling that I have been talking about these vortex filaments since the first time I came here. I don't remember when it was, but a long time ago. So I think we make some progress on the business, but very, very slowly. But at least there is some progress. All right, so let me start with a small summary of the talk. I will speak about the Talbot effect in the linear setting, then the example of a nonlinear dynamics where the Talbot effect also happens, and this is a joint work with Valeria Vanica and Francisco de la Hoz. And then unfortunately, the talk will be very speculative, and that means that I will use plenty of pictures. That's the only thing I can offer you. And the idea is to try to answer the following question, which is, has the Talbot effect anything to do with turbulence? Okay, so I guess at some point I will have to tell you what is the Talbot effect. That is the first part of the talk. And what it is not clear at all, at least not to me, is what it is turbulence. All right, but there are kind of some hints of what people say that should appear in turbulence, which are things like the key word is cascade, that I'm not sure what it means. There is another one which is intermittency. And definitely also some kind of randomness. All right, so let's start. So what is the Talbot effect? If you go to Wikipedia, this is what you can find, and I will read with you. The Talbot effect is a near-field diffraction effect, first observed in 1836 by Henry Fox Talbot, and it goes more or less as follows. When a plane wave is incident upon a periodic diffraction grating, the image of the grating is repeated at regular distances away from the grating plane. The regular distance is called the Talbot length, and the repeated images are called self-images or Talbot images. Furthermore, at half the Talbot length, a self-image also occurs, but phase shifted by half a period. At smaller regular fractions of the Talbot length, sub-images can also be observed. For example, at 1/4 of the Talbot length, the self-image is halved in size and appears with half the period of the grating. Thus, twice as many images are seen. At 1/8 of the Talbot length, the period and size of the images is halved again, and so forth, creating a fractal pattern of self-images with ever decreasing size, often referred to as a Talbot carpet. So one could think, when going back to this kind of word, these words, where that when you go to talks about turbulence, they try to convince you that it's a way of going from large scales to small scales or vice versa. Well, you could imagine that this could be a way of describing it, because this is the picture of the Talbot effect. So this is, you can imagine that the plane wave comes through here. You have the periodic grating here, right? So it's in here we have, say, 4 delta functions, if you could imagine. All right? So you could say that this is the relevant length, but now this relevant length becomes this, and it could be smaller and bigger, and so on and so forth, right? The only problem with this is that this is a linear phenomenon, and it's very hard to imagine that you are going to describe turbulence using linear models, all right? Anyway, this is the Talbot effect. So in half of a period, you see, you have again 1, 2, 3, 4, but they are shifted by half of a period in space. And a quarter of a period, you have now 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. You can also see all these symmetries, which are lines going from one point 2 to the other one. And these symmetries will be fundamental to understand why the Talbot effect is true. So if you keep going to Wikipedia and you try to see what is this issue of the diffraction, then essentially there are two kinds, or two main kind of diffractions. One is the Fraunhofer diffraction, which is that you have your wave coming from the left, you have your screen with, say, a hole here, and then you try to see what happens far away. And if this distance is, say, infinite, then what you see here is essentially the Fourier transform of the characteristic function of this hole. This is very easy to see. Just use the fundamental solution of the Helmholtz equation and look at the asymptotics of the corresponding integral. And in fact, that is true. The leading term is the characteristic function of this set. Of course, what happens here is that the only thing you can measure is the absolute value, right? So you only measure the intensity. So in terms, if you are dealing with the complex functions, which is the kind of thing that eventually we'll use, the only thing you see is the absolute value. You lose completely the phase. But you remember in the explanation I spoke about near field, and this is the near field. So this is at infinity what happens, and in between, when you look at the oscillatory integral that appears in the solution of the Helmholtz equation, well, you have to make expansion, and then if you go to infinity, you only take the first leading term. If you are not so far, you have to take the next term, which is a quadratic phase. And this is called the Fresnel diffraction, right? And then, well, if you forget about the constants, put a lot of imagination, eventually you can try to describe what you are saying using the free Schrödinger equation, okay? Where the two variables, remember, the two variables before were this that we call C and this that you can call X. In what follows, in the Schrödinger equation, this variable will become time. And this is what I am calling S, all right? So this is the equation. So you can imagine that the screen starts at time 0, and this could be the initial value problem you want to solve. You want a jump function, right? You want 0 and 1, but instead of putting 0 and 1, I put negative 1 and 1 because it's easier for my purposes. So the question is, what is the solution of this initial value problem that, of course, we all know, with periodic boundary conditions? And this is very easy solvable using the Fourier series. I mean, there is no secret in this. And I want also to add another example, which is this one. I still have a jump function, but the image, in terms of the complex plane, is 4 points, right, which are the corners of a square. All right, so let's try to see what is the solution of this problem. And if you go to, say, Mathematica or MATLAB, this is rather easy, and this is what you see. So here time is pretty small, it's 10 to the minus 5. And what is this picture? This picture is I give you S, and I compute phi of St. So this is a real parameter, this is a complex number, so it's a point in the plane. So this describes a curve in R2, which is the one you see. And what happens here is that the time is extremely small. So if you use, for example, a spectral method, say with 10 to the 5 frequencies, you are in a time which is small enough such that the waves don't have the time to reach the boundary. So what you are seeing here is nothing but the solution for the initial value problem, but in the full line, which is negative 1 and 1. And in that case, it's very well known, which is this picture, and this is nothing but the Cornu, what is called the Cornelia spiral that was invented by Cornu to describe Fresnel diffraction. So this is like the solution in full space. Of course, if you go to a larger time, then the thing changes dramatically because the waves have the time to reach the boundary, say the full period, and they start to interact with each other, and then the dynamics is very different. Is this picture that you see here. And now if you instead of having two, of course, this is one of the eyes of the spiral, and this is the other one, which is the -1 and the 1, which are the initial conditions, right? The same function. If you change to the other initial condition, now you have the 4 points, which is 1, I, -1, and -I. Well, yes. All right? So this is what happens at the linear level. So now let's try to understand the Talbot effect analytically. So really, now I have to change the initial condition. I put the other one because it's much easier to understand what's going on at the numerical level. But if you really want to describe the picture I showed you of the Talbot effect, you are dealing more with periodic delta functions at time 0. And you put the intensity, say this one, which is related in this case, and this is because I will need it later on, not because something that I really need. This is a linear problem, so to change this number is completely harmless. So the point here is that the periodicity is 2 pi over m. So I want to find the solution of this problem. Of course, we know how to do this, again, using Fourier series, but I will do it in a kind of complicated way, because I want to extend the method to the nonlinear setting. And of course, in the nonlinear setting, to use Fourier series is not that simple. So what I'm going to use are the symmetries of the problem, which in this case are the so-called Galilean transformations. And these Galilean transformations are related to the lines we saw in the picture of the Talbot effect. You give me any real number, I generate this line. And what happens is that if I construct, you give me a solution of this problem, you give me this k, and I construct this new function, say phi tilde. It turns out that if I plug this expression in the equation, I obtain another solution. Okay, so this is a way of giving one solution to generate another one, depending on the parameter k. But now, what is the initial condition for this new solution? Well, I make t equals 0, and this is what I get, right? K. Now I'm calling it 2 pi. Now k becomes 2 pi j m. Why? Because if I make this choice, when I look at this initial condition, this guy is the same as this one, right? Because I am computing the delta function there. And the delta function multiplied by 2 to the pi ix is the delta function. So the initial condition is invariant under all these transformations. I mean, not all of them, just the integer ones. As you can imagine, this has very big, very strong consequences. So let's try to see which are these consequences. So this is what I mean, right? That because the initial conditions are the same, and of course this is a linear problem, you have uniqueness, so this has to happen. All right, so let's start. I define the Fourier coefficient in the usual way, and now instead of writing psi in this, with this expression, I use the one I have just proved. So this has to be true for all k. Then I get this guy outside, and I do nothing else. Now I do the change of variable, s minus 2 mkt equals s, and I then, this is what appears, and then this guy goes outside again, right? And I obtain this phase outside and this integral inside. I mean, this is simple algebra. But if you put everything together, the conclusion is that the j Fourier coefficient is related to the j minus k Fourier coefficient times this phase, right? So now you make j equals k, and this is telling you that if you know the 0 Fourier coefficient, you know the k Fourier coefficient. So you know all of them. And of course, this becomes 0, so it's harmless, and this becomes j squared, which is what you expect. So the conclusion is that the solution has to be this one. Well, in terms of the Fourier coefficient. So now the question is, what is this number that depends on time? Well, you plug it into the equation, you compute it, and it's very easy to see that it has to be 1. All right? So the final conclusion is that this is the solution. Something, of course, we knew from the beginning. All right? All right. So this is the solution. is the Fourier series. Well, you see, a consequence of this fact is that when I make t equals 0, I obtain Poisson summation formula. Because on the left, I can write this as a sum of periodic deltas. And on the right, I write it as a sum of as a Fourier series. Good. So now, in order to prove the Talbot effect, remember that the distance to the screen was the time, and everything was about considering rational distances from the screen. So, of course, I have to take into account the periodicity, so the rationality is here, modulus the periodicity. And the m squared has to be m squared, cannot be m. Now let's compute what happens at the solution at this time. So I write it. I'm going to keep this because eventually I will need it in the nonlinear setting. But now this is 1, so you can forget it about it. So I write the time, which is this, and it will be multiplied by mk squared, remember. Right? And this is in S. So of course, now the m's cancels, and the only thing I obtain is this. And now the elemental idea, which is very simple but very useful, is that I'm going to write this sum, which is just in k. I'm going to write it as a double sum. You give me q, and then the integers, I write them as qk plus l, something I can do. You give me k, and any integer, of course, can be written in this way. And now the sum becomes a double sum in k and in l. And now what happens is that when I expand this square, the only thing that remains is L squared, because the other ones are multiples of Q, and then of course they give you 1. They give you 0, multiples of 2 pi I, and then the exponential is 1. So this is what I get. Right? It's just the sum in L of these quadratic faces times this. And remember that this expression is nothing, is related to the delta function, and what we had before was this, which meant that we have a periodicity given by capital M, which was our big scale. It turns out that now we have created new scales, right? Because it appears a new periodicity, which is M times Q. All right? This is the first thing. But these new deltas are multiplied by these guys. Okay, and who are these guys? Well, this is a trigonometric series. I'm sorry, this is what yeah, this is fine. So what the conclusion is that at this time, this was the initial condition, and I obtain all these delta functions. You see the periodicity is now m over q, 2 pi divided by m over times q, multiplied by a guy that was the sum I wrote before, that now I am calling it capital G, at the point minus PMQ, and I will write in a minute what is capital G. But this is the Talbot effect, because at half of the distance, instead of having m deltas, now I have 2 m deltas. And a quarter of a distance, I have 4q. All right, so this is what I had. I have 4 deltas. Right, I had it here, 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 and here. And half of the distance I have the same ones, but I have some others in between. Okay, the 8th one. But they are multiplied by these numbers. And these numbers, as I said before, are these trigonometric series that are called Gauss sums, because they were computed by Gauss. And of course, they are very well understood. And this is the recipe for these Gauss sums. Typically, they are square root of q. And if q is odd, otherwise it could be a square root of 2 times q with some phase. But they can be 0. For example, if q, no, they can be 0 under these conditions. So what happens in half of a period? In half of a period, q is 2. Right? And q divided by q is 1. So if I call this was m equals 0, 1, 2, 3, this will be 0, 1, 2. Now 0 is not congruent with 1 modulus 2. So I have to erase this one, and this one. And of course I obtain the Still 4 deltas, but they are shifted by half of a period. You don't need to go to the Gauss-sums to prove this, because this is a consequence of a very simple fact, that if I, this number, k times k plus 1, is always even. Okay? So now you believe me that we have proved the Talbot effect. These phases, we don't care about them, because as I said before, we are only computing absolute values. So in the case of the Talbot effect in the linear problem I am mentioning, the phases do not appear. All right? Good. All right, so let me go a little bit further. I need some extra thing coming from the linear problem, which is that I'm going to consider the, I'm sorry, this would be from negative infinity to positive infinity, so there is a misprint here. So this was the solution I had at the position s equals 0, because I only have the quadratic phase. So this is the solution at s equals 0. So I fix now the position s equals 0 and make an integral in time. In terms of the Fourier series, this is completely harmless. It's just divide. Of course, I have a constant, the constant of integration, but it's just to divide by k squared. And this gives me another trigonometric series, which now is very easy to prove that it is convergent. The previous one was not convergent at all, of course. This one is convergent, so the function that goes from t to phi of t, which will be, again, you can visualize it as a curve in R2, this function at least is continuous, right? And the picture of the function is this one. This is a very well-known function which is called the Riemann non-differentiable function, which was proposed by Riemann as a function which is continuous but has a derivative at no point. And this was not true, because precisely at some points the Gauss sum is 0. This was later on proved, I think, by Hardy or some of these well-known guys. But it's almost true. So it has derivative just in those points, which is, they are, of course, of measure 0. And as you see, the picture is kind of fractal, right? It's, in fact, it was proposed by Duistermatt, and he almost proved it, but he didn't quite get it, that this is not a fractal. It is what it is called a multifractal. So a multifractal is a different thing than a fractal. So what is why is this a multifractal? Well, you want to classify the points t according to the Holder exponent. So you look at the points according to their regularity. You look at the Holder regularity. And now you classify the points by the exponent of the Holder regularity. You give me an alpha exponent of Holder regularity, and you put in the same set all the points that have this given alpha regularity. This is a subset of the interval 0, 2, and now you compute the dimension. It turns out that it is a fractal and it has a dimension. But the dimension depends on the alpha exponent. So the dimension of the fractal depends on the Holder regularity. And it turns out that the Holder regularity is something in between 1/2 and 3/4. Okay, so the alpha, which you can take, well, it does not completely true, because there are some particular members which are precisely those ones where the Gauss sum is 0. The Holder regularity is in this set, so you generate the corresponding set. And the question is, what is the dimension of this E alpha? Well, it turns out that I think it's 4 alpha minus 2. It's just a very easy formula. But this formula, which was proved by Jafar, fits what is called a Fritz-Parisi conjecture, which is a conjecture that was proposed by Fritz-Parisi to describe turbulence, in particular intermittency. Really, you are looking at you will see it. It's you look at the trajectory, say, of a one point, and you really want to measure the alpha, the Holder regularity. and you want to see which is the dimension of, it's precisely that, the dimensions of the corresponding sets. All right, so this is about the linear problem. Let me say a few references. So, well, the Talbot effect, in fact, was explained essentially the way I have mentioned it by Rayleigh. So that means many years ago, Lord Rayleigh. But as far as I know, the only paper where everything is written with proofs, or not complete proofs, but I mean many facts, is a paper by Berry and Goldberg that appeared in Nonlinearity. Is the first paper of the first issue of Nonlinearity. Okay? And then Duisterman, I already mentioned it. Skolkov is a guy that always in fact, I was in a talk given by him many years ago in Vienna, and he put these spirals we saw at the beginning and say this has to do with turbulence. Okay. And he has a paper mentioning this kind of things. Then Jafar, I already mentioned it, and also, so Jafar was to try to measure the multifractality, if you want, when you fix S and you look at the trajectory for time. Another possibility is the spirals I showed you at the beginning, which is that you fix time and then you see the curve for different S. And this is an open problem. Nobody knows how to prove the dimension of these guys. And Kapitansky and Roniansky did, in the linear problem, did some work on this. Olbert did some work on the nonlinear situation for KDB. Well, for example, that means 80 function. This kind of thing is still true, where you put, I guess, k squared, or I don't remember, k squared times k squared plus 1 is still an even number, and this property is still true. And finally, Erdogan and Chiraki's proved theorems. This was at the numerical level. But for the cubic nonlinear Schrödinger equation, but everything they do, I mean, for the semi-linear Schrödinger equation, but everything they do is sublinear, is subcritical. So what they prove comes from the linear problem. And what Pachi and I, Francisco de la Hoz and I did was at the critical level. We generate new nonlinear guys. All right, so now it's time to go to the nonlinear setting. Okay? So remember that at the linear level, I had 3 levels of regularity. I start considering the sine function. So that means, say, -1 for s minus smaller than 0, and +1 for s minus pi, and s bigger than 0, smaller than pi. But it turned out that to describe the Talbot effect, I had to consider the periodic delta. So this was one level of regularity. This is another level of regularity. And finally, I consider the integral in time of these guys, which means 2 integrals in space. So I was considering essentially as initial condition absolute value of S. Right? Because I was integrating twice in space. Because I integrated once in x. In time. I integrated once in time, which means I am integrating twice in x. So these are the 3 levels of regularity. The jump function, the derivative of the jump function, and the primitive of the jump function. Why I'm saying this? Because in the nonlinear level, to pass from one to the other one is not so straightforward. Right? At the linear level, you just go to the Fourier expansion and you multiply or divide by the k, or k squared. So let me start with this level of regularity. I want to give you an equation which is similar to the free Schrödinger equation, but where the homogeneity of the problem, the equation is critical precisely at the level of the jump function. Okay? This one. And you have to imagine always, you always have to imagine a periodic boundary conditions. So it's a periodic initial condition. So what is this? This is an equation. T now is a unit vector, and I still have variables, spatial variables, which is S, and time variables, T. Right? So I'm saying that this is a vector on the sphere, and I am saying how it evolves with time. And it evolves according to this law. I compute the second derivative, I and I do the great wedge product with the tangent vector. But this can be written in this way. I am computing the second derivative, and to do the wedge product, I am doing two things. First, I project on the, it has to be orthogonal to the tangent vector, which is the normal vector to the sphere. Have the sphere, right? And I have the tangent vector, and the tangent vector is, is the normal to the sphere. So to do this is to project on the tangent plane, so that means that I compute the covariant derivative, but of course I am also doing some rotation, because it is the wedge product. And this is typically written in this way. So I am computing two derivatives and multiply by little I. And this is, of course, the Schrödinger equation. The only difference is now that the target is not the complex plane, but the unit sphere. And this is where the nonlinearity comes. It is not flat. It is the sphere. Right? So what is, what is this initial condition? Is to consider just something that has two values, two vectors. Now I want to go up and consider this, which is to integrate in x. And that I do it just by pure integration. And I obtain another equation that now the unknown, I call it capital X, right? Which will be, you can understand capital X as a curve in R3, such that the tangent vector is capital T. Okay? So X, this is T, and XS, the derivative with respect to S of X, is the tangent vector, capital T. And it's very easy to go from this expression to this one, because it's just to differentiate with respect to S. Then when the derivative falls here, you get 0, and when the derivative falls here, you get this. Okay, so this is rather simple. Now, if you use Frenet system of equations, you can write this expression, which is just given in terms of partial derivatives in geometric terms. And what you get is very easy, is the curvature times the binormal. So this is a flow that I have been talking about this flow in this place for many years. That's the binormal flow. So you have a flow of curves in R3, which is given by the following law. You go to, in order to see the velocity, you go to a point, you compute the curvature of the point, and you move with that speed in the direction of the binormal. So in particular, if you start with a ring, which has a curvature which is constant, you will obtain a ring that moves with velocity which is the inverse of the radius, and the direction depending on the orientation you give to the ring. If you have a straight line, it will not move. And if you have an helix, it's very easy to see that you will still have an helix. The ring is the typical example of a smoke ring, and this is where the vortex filaments do appear. And a smoke ring is the one you create when you put a smoke in your mouth, and you put a French mouth, and then you hit suddenly, right? This is a smoke ring. So this is this level of regularity. But now I want to go down to this level of regularity, which would mean the delta function. And this is not that simple. And it turns out that you need to use a nonlinear change of variable, which is the one you see in the slide. This was invented by Hashimoto in 1971. So given the curvature and the torsion, this is the torsion, so the face is the torsion, the primitive of the face is the torsion. You generate a complex number, which is this psi. And now the question is, if the curvature and the torsion are given by the curvature of the torsion of this curve, capital X, that evolves according to this law, what is the law for the psi? And it turns out it is the cubic NLS in 1D, where this A of t is real, and from the PDE point of view is completely harmless. From the geometric point of view, it's important because it gives you some, and also from the PDE point of view, because it gives you some degree of freedom that you can use, and it really plays a role. a good roll. So this is the setting at the nonlinear level. 3 equations. The Schrödinger map, the binormal flow, and cubic NLS. Everything 1D, and we are considering periodic boundary conditions. Right? So now, one corner. So I want to put myself in the case of, say, 1, which was essentially the same as the first picture I showed of the Cornelia spiral. It's essentially at the same level. First, one thing, just one jump. And then we will deal what happens with the periodic conditions. So 1 delta means, at the level of the curvature, 1 delta means that you have a corner at the level of the curve. Right? That's what I mean. So I want to solve the equation for the capital X for 1 corner. So that means that you have some dilation invariance. So you look for, instead of now Galilean, now you look for the dilation invariance. So you look for self-similar solutions according to dilations. And this is the recipe, which is very easy. In terms of the tangent is this. Then you do the math, which is a very simple thing. So you end up, which is the equation that the capital T, I'm calling capital T to 2 different things. So this is a nonlinear ODE, and you want to solve it. And you solve it using Frenet frame, and you do the math, and the conclusion is very easy. The corresponding G that gives you the self-similar profile is characterized by the fact that the curvature has to be a constant, and the torsion has to be S over 2. So the 1-parameter family of curves are given just by the curvature. Of course, the corner has only 1 parameter, which is just the angle. Right? So this is the 1 parameter, the free parameter you have to consider, up to translations in space and up to rotations, of course, because the equation is invariant under rotation. So now the question is, what is the curve which has this property? You go to, this was proved by Batke, although in the setting of capital T was proved like 8 years before by some other people. So now you go to Mathematica and you tell the machine to print the curve that has the curvature as a constant and the torsion S over 2. And you do the self-similarity. The self-similarity means that this could be imagined that is the self-similar pattern, so the capital G, and you do all the others, and this is what you obtain, of course. You obtain that at time 0 you create a corner. And you can go forward in time or backward in time, because the equation is reversible in time. So you can imagine that you start with 1 corner, and what you generate is something which is regular with all these oscillations here, and then you reproduce it by self-similarity. Or you can go backwards. You start with this nice guy, and you do the self-similarity, and you end up with this corner. And you see it from the other side. You see that the corner immediately shifts from the plane that contains the 2 lines. All right. So if you go to the tangent vector, you obtain a spiral on the sphere. This would be one of the vectors of the jump function, and this is the other one, right? This is one of the directions, and this is the other direction, right? So this is the corresponding spiral, which is the Cornu spiral, but instead of the plane, on the sphere. It's precisely that. So the case of 1 corner, we understand it. Moreover, we understand it really, not only with pictures, but we also have a theorem. And this theorem, I'm going to explain it again using a picture. And this is the picture. So what I plugged before, I mean the previous slide, the 2 previous slides, was the solution, say, for T positive, or you can imagine this is T1 and I go up to T0, or this is T0 and I go to T1. And I generate this. But the equation is reversible in time and invariant under rotation, so it's very easy to compute which should be the solution for negative time. It's just to change the orientation of these guys, and this means that you make a rotation. So you do the rotation and you obtain these other guys. So in this artificial way, I have constructed a candidate for a solution that it is nice at time -1, generates a corner at time 0, and evolves again into a nice corner afterwards. All right? So I start with this, which is the cell-similar pattern. I generate the corner, and then I go back to the regular guy. You see, if I take the origin, say the origin would be there, the trajectory of the origin, let me put the previous one. You see, the trajectory of the origin at t positive is this one. Right? What I have done in the other slide is to make a rotation of this angle. So I put it here. So it will be like this. So the trajectory of the origin will make a kink. You see, it will make a kink. Goes in this direction and then up. So, but this is completely artificial. Nobody tells me first that this is a solution, and second that if it is a solution, in what sense is it a solution? It is unique, it is stable. Well, this is what I proved with Valeria. It took us some time. But this is the theorem, that this is not just an artificial object. It is something that exists, and it is stable, and it is unique in some sense. All right? Of course, that means that the process of creation and annihilation of a corner is stable. I start with something which is nice, I create a corner, and I go back to something which is nice. It's important to say that at the level, this is at the level of the curve, and even at the level of the capital T. But if I go down all the way up to the cubic NLS, I cannot make sense of the equation. So it is not true that the delta function is well posed as an initial value problem for cubic NLS. So that means that I can start with something nice, and then I go to time 0, I create a delta, but I cannot, in principle, I cannot continue. I create a singularity that I cannot continue. But if I know that this equation comes from the tangent vector, meaning that it comes from a geometric equation, I find the way of continuing the solution after the blow-up has been generated. So this is a continuation after blow-up, where the blow-up happens at the level of cubic NLS. All right? Good. So now let me put a bunch of delta functions. That means that I am considering as a curve a regular polygon. And to describe the regular polygon, what I give you is just the curvature, which is a periodic array of delta functions. But we know that for cubic NLS is also invariant under Galilean transformations. So I can use exactly the same trick, and I will obtain the same conclusions, right? Which means that my solution, this is exactly the same, right? The reason why I copied here, because now it is not just the absolute value of what I care of. I care about everything. The absolute value will be the curvature, but the phase will be related to the torsion. So this is the difference from the linear problem to the nonlinear problem. Having curvature or not, having a flat target or not having a flat target. All right? So that means that I'm going to generate, if I start with, say, a triangle, which means capital M equals 3, I will generate new corners. But because this guy is, in principle, is not going to be 0, these corners will not be in the same plane. They will be in different planes. All right? Of course, the only thing is I have some problems on how I integrate things which are jumps, and I'm multiplying by delta functions. But this is very easy. It's just to compute. So this is the Frenet frame written in what is called the parallel frame. So I have to multiply delta functions, but things that have jumps. Of course, you can do it. And the only thing you have to do is to compute the exponential of the antisymmetric matrix that gives you this rotation. And then the way of constructing the polygon is that you give me one side, and I pass to the next side by the corresponding rotation. But remember that even at the linear level, we have the 0 Fourier coefficient that was not fixed, was depending on time. So how do I fix that in here? Well, I'm generating a regular polygon. What I want is that the regular polygon is closed. So that means that I have to multiply. So this is what I was saying, right? That you pass from this side to the other one just by a rotation. And in order to close the polygon, I have to multiply all these awful matrices, and eventually I will have to get the identity. So this turns out to have this consequence. The corresponding matrix that you obtain by multiplying all of them has to have this property, and this is the recipe. the thing you were missing is encoded here. The zero Fourier coefficient is encoded in this expression that you see here. We don't know how to prove this theoretically yet. This was proved numerically. So this is a conjecture. All right, so now I have constructed the candidate for a solution. Right? I use the invariance and I say the solution should be this one. But I have no idea why this is a solution. Then what I do is I use a numerical algorithm, I use some numerical code, I run the equation, I see what happens for my initial condition. Here, the initial condition is a triangle, and this is the time. So the number of sides is 3. This is the time, and these are the 3 components of the tangent vector, green, red, and blue. This is the theoretical solution, the one that we claim that should be the solution. And this is the numerical one, because you can see the Gibbs phenomena. And amazingly, they fit. All right? But let me see what is the the shift in half of a period. So imagine that you start with a square, right? M equals 4. So in half of a period, you should create another 4 corners. But we know, because of the Gauss sum is 0 there, that the ones you start with become 0, because the Gauss sum is 0. So this square should become this square. And if you do the triangle, because the arc length is preserved, you will generate this, and then it will be the same kind of triangle, because the arc length has to be preserved, but the corners have to be in the half of the sides. So the triangle has to be shifted. This is what we claim it happens. Well, this is, for example, that the dynamics can be really weird. This is for a time which is a rational with a huge denominator. And as you see, well, it seems that it's kind of a reasonable polygon, but it is not. And this is what happens when you compute the trajectory of one corner. Say you compute the trajectory of this corner, which is exactly the same as I did for the Riemann non-differentiable function. And this is for m equals 3. There is red and blue, although you don't see the difference. And this is for m equals 4, and they are different. That's what I was saying, that I generate new nonlinear guys. They are not the same. They are not the same. This angle is different to this one. And the new fact that we have proved numerically again is that it is the one that the self-similar solution tells you that has to be. Remember, I told you that in the case of the self-similar solution, if I follow the trajectory of the center, it was a kink, is precisely this one. I come from here, say at negative time, and follow here. And it is precisely the one of the self-similar solution. And this is for more of them. And numerically, we prove that when the number of sides goes to infinity, then you go to the Riemann function. Here is just a normalization so that you can compare this with this, because as you see before, in the nonlinear case, you start and finish at different points. We don't know if this is a multifractal or not. We don't know what is the Hausdorff dimension of this, and we don't know if the Fries-Parisi conjecture is true. Okay? So now about pictures. And I have, say, 7 minutes of pictures, all right? First of all, this is to convince you that more or less, although binormal flow appears as a very crude approximation of Euler equations, it seems that captures part of the business, right? This is the flow behind a delta wind, and you are putting this is in water, and you're putting some ink to see what is the turbulence or the vorticity. And well, and at least at the qualitative level, they look similar. This is another picture where, of course, again, you see the same kind of horseshoe structure with all these helices. You have the similarity. But this could be a first picture to understand what is the difference between a laminar flow, which would be this one, with something that starts to be a turbulent flow. Okay? So this would be laminar. This would be turbulent. But if you want to find a definition of what is turbulent, then you ask the experts. And then I ask the Spanish expert, which is Javier Jiménez Sendín, who is in the engineering school in Madrid. He's also a professor at Stanford. And this is his definition of turbulence, right? So this is a jet where how do you call this in English? This is the okay? And the velocity is not big, then it's essentially laminar. And when the velocity is much bigger, it becomes to be turbulent. It doesn't look too much turbulent, but this is more or less what is the definition. So why do I put this? Because I'm considering just a jet. It's like the smoke ring, right? Okay, so is this now true? How can I generate a smoke ring with corners, right? Well, this is the experiment of the garage, where, of course, I cannot do it with my mouth because it's a little bit difficult. But you go to YouTube and you always find the solution. What is you have to do? And this is what you have to do. You generate your car box, and of course, in here you don't see, but there is a hole which is in the other position. You put the smoke and you just hit. And then you see the switching of the axis. All right? And this is really, I mean, you can repeat it and it happens. Huh? So the question is if between this position and this position you can detect something which has, say, 6 corners. Of course, the corners are not corners because this you have a viscosity and they are never a corner. Well, this is what we were able to get. That, of course, you don't see here. You see it a little bit better in the computer. We have reproduced this 2 weeks ago with another machine which is faster. And, well, you can, yeah, I believe it, that there is something with 6 sides. Then when we did this, say, come on, this has to be in the literature. And then you go to the literature, and it turns out that the keywords are non-circular jets. This is a paper, survey paper of the 1999, and it turns out that these non-circular jets were very much on fashion starting in the mid-80s and all through the 90s. So this is a review. And for example, in this picture, they see the flow patterns associated with non-circular jets involve mechanisms of vortex evolution and interaction, flow instabilities, fine-scale turbulence, augmentation, and blah, blah, right? And in here say, experiments reveal a complex vortex evolution and interaction related to self-induction and interaction between azimuthal and axial vortices, which lead to axis switching in the mean flow field. And these are the pictures they put. Okay? Of course, it depends very much how you hit from the boundary. Is the picture I put. If you don't hit too strong, then nothing happens. You have to hit strong enough so to really create a vortex. And you have the going up, going down, and here's also another hint that what happens is not symmetric, so that means that the corners cannot be in the same plane, which is what it has to be. Then you go, there is another paper which is, well, there are plenty, huh? But this is at the, at the numerical level. And again, non-circular jets, and in here, flow visualization could show the large scale coherent structures. This is another of the keywords that these people really love, in both corner and non-corner jets. The axis switching phenomena is captured, depending on some aspect ratios, and this is the picture that you see, right? So this is the starting thing, that if you start with this shape, you end with this shape. If you have the square, well, this is what you have, and this is for the triangle, and well, you can imagine there whatever. This is an old thing. All right, and to finish, I want to show you this, which is if the definition of turbulence is just a jet through a pipe, this is the jet, right, where it has a square. And this is the way these people describe what they see. Right? You see immediately that the coherent structure they mention are these kind of horseshoe structures that, of course, do appear in our case. For us, a corner is not a corner. It's really this horseshoe at different scales. And, well, if I have to describe somebody what I see, it is not so far from this, right? You see, because, of course, each corner is a horseshoe, and you generate more corners. And then, well, what is this? Who knows, right? So this is the question. Can you really explain this phenomena saying that it is the Talbot effect which is behind all this? And to finish, the randomness, I didn't say it, the randomness, it is in the phase. That only appears in the nonlinear problem, because the phase was the torsion. In the plane, it's just the absolute value and you don't care. So the torsion only appears when you consider the geometric problem. And if you look at the torsion, this torsion, and this is another paper with the Talbot, we prove that it is one of the examples, classical examples to generate pseudo-random numbers in the computer. Okay, so the whole process is deterministic, but if you want to describe it, better you forget about determinism and you try to see it as a random process. And finally, this is the thing I want to finish. The cascade, what I wanted to explain is that it cannot be as simple as creating big scales or small scales, because this is also done at the linear level. The Talbot effect happens this. And of course, you're not going to explain turbulence just with the linear level. So I guess that the cascade is more in the direction that the energy goes from higher modes to lower modes. This model, from that point of view, has a lot of limitations because it is it's a completely integrable system. So it cannot be an issue for a large regularity. But it is not clear to me what happens at the critical regularity, in terms that instead of measuring it in terms of h1 half dot, you could also consider L infinity. And if you do the stereographic projection of the tangent vector, this you see that the L infinity norms can grow as much as you want and can become as small as you want and blah, blah. And this does not happen at the linear level. It was precisely this picture. Let me finish with this. Huh? I promise this is the last time. This is what I wanted to show you. You see, if you do the stereographic projection of this guy, because your polygon was in the equator, the stereographic projection is going all up to the north pole. So if I look at the equation, which is also very well known, it's some nonlinear Schrödinger equation with derivatives, which is still a completely integrable system, the infinity norm can become as huge as you want. Although at time zero is completely finite. So thanks a lot for your attention.